Hi everyone. In this lecture we're going to continue our investigation of series, and in particular we're going to look at how to use integrals to test whether a series converges or diverges. Let's just recall what a series is and this question of convergence. So for example, we'll consider the series 1 plus a half plus a quarter plus an eighth plus ... So each term is half of the previous one. So this is a geometric series, the common ratio being a half in this case. Now what does it mean to add up infinitely many numbers? Well, we said that to make sense of that, what we're going to do is convert this to a question about sequences, in particular the sequence of partial sums. So we're going to look at the first term, that's the first partial sum. We're going to look at the first two terms, add them together, and that's the second partial sum. Then we'll add the first three terms, third partial sum, the first four terms, the fourth partial sum, and we keep going. So now this question about adding up infinitely many numbers, we've converted to a question about a sequence of numbers, the sequence of partial sums. And the question is, do these partial sums get closer and closer and closer to some number? In other words, does the sequence of partial sums converge? In this particular example, we have a closed form for our partial sums. It's 1 minus the common ratio to the k plus 1 all over 1 minus the common ratio. So this is because it's a geometric series, and the kth partial sum of a geometric series can be expressed in terms of the common ratio in this way. Now, does the sequence of partial sums converge? Well, this is a question as to whether the limit as k goes to infinity of s sub k exists. And in this case, 1/2 raised to the k plus 1, as k goes to infinity, since 1/2 is smaller than 1, these things get smaller and smaller and smaller, so that goes to 0. So this approaches, or heads towards, 1 over 1 minus 1/2, which is equal to 2. So our partial sums get closer to 2. So I add up a bunch of finitely many terms, and I get some value, and then I do the next term, I get another value, which is closer to 2, add on the next one, even closer to 2. I keep adding on these terms, and I get closer and closer to 2 as I like. So if I imagine adding up infinitely many terms, then I'm converging to the value of 2. So I can get to close to 2 as I like by adding up as many terms as needed. So we say that the series converges to the value of 2. Now, in the geometric series case, we're able to not only determine convergence, that's whether the common ratio is smaller than 1, or divergence, the common ratio being bigger than 1. And we can determine exactly what it converges to, such as in this example. The problem is, for a general series, it's really difficult to decide what the series converges to exactly, even if you know it converges. That's a difficult problem. So finding the value to which it converges is a difficult problem. In the geometric series case, it's fairly straightforward, but in a general series, that's a difficult problem. So we're just going to be content with asking the question right now is, does the series converge or does it diverge? So let's look at this example. Sum of 1 over n squared. I want to know, does the series converge or does it diverge? Not what it converges to if it does converge. I just want to know, does the series converge? I don't care what it converges to at this point. Just want to know, does it converge? Well, here it's saying compare with this integral. So the idea is I have a question about something I don't really know anything about, the sum of the series. And I convert it to a question I do know something about. What's the value of this improper integral? Well, I know that this improper integral converges. And it converges to 1. You can actually just work it out, find the antiderivative, and then evaluate the improper integral. So you'll find that the value is 1. So what that means is the area under the curve is 1. Now I want to figure out something about this series. Well, what I can do is I can say, well, I interpret the improper integral as an area of a region. Maybe I can interpret the series as the area of some region and make a comparison between the two. Now, if I know the area under the curve is finite, my best bet is to try to interpret this series as the area of something that sits inside that region. So let's look at that series. It's 1 plus, plugging 2 in, that's a quarter, plus plugging 3 in, that's a 9th, plus a 16th, plus ... Now, if I look at this first interval of 1 to 2, if I pick a rectangle using the right-hand endpoint that sits below the curve, What's the area of this rectangle? Well, plugging 2 in is 1 over 2 squared. That's a quarter. So the area is base, which is 1, times height, which is a quarter. So that area is a quarter. Oh, so that's that first number there in my series. I do it the same thing for the next interval, and I get the area is a ninth. And I do the next interval, and I get the area is a 16th. So what I'm doing is I'm recognizing that, ignoring the first term, but from the second term onwards, the sum is actually the area of these rectangles. And that's nice because that tells me then that this has to be smaller than 1 plus the integral from 1 to infinity of 1 over x squared dx. So I'm using the fact that the rectangles sit inside the region under the curve. And so the 1 plus the area of the rectangles has to be smaller than 1 plus the area under the curve. What's the area under the curve? Well, that's 1. So what we have is that our series, n goes from 1 to infinity of 1 over n squared, has to be smaller than 1 plus 1, or 2. So our series has to be smaller than 2. Does it converge? In this case, we have that, yes, it does converge. Therefore, the series converges. How can I conclude that once I know that the series has an upper bound of 2? Well, let's think about it. What are the options for this series? I'm adding up positive numbers, an infinite number of positive numbers. So my options are either the series blows up to infinity. I'm just adding up too many, infinitely many numbers that are just too big to converge, so it goes to infinity, or it heads to some finite number. Well, this inequality tells me I can't possibly go off to infinity because my series has to be smaller than 2, has to sum to a value smaller than 2, and so therefore it converges. What's underlying this jump from here to here is really the monotone sequence theorem. The monotone sequence theorem is at play here. So let's just make a note of this. Note that for this example, the sequence of partial sums is strictly increasing, so it's monotone, and the sequence of partial sums is bounded. In particular, we've shown it's bounded by 2. That's what we use the integral to get. So, by the monotone sequence theorem, this sequence S sub k converges. And that's exactly what we need in order to conclude that the series converges. Convergence of the series is explicitly defined in terms of the convergence of the sequence of partial sums. So we have the sequence of partial sums converges, therefore the series converges. So we're using the monotone sequence theorem in the background here, is really the point. So we have that the series converges. What does it converge to? I don't know. We don't know at this stage. All we know is that the series converges to a value smaller than 2. And we can sort of say, well, it has to converge to a value that's bigger than 1, actually bigger than 1 plus a quarter. Well, actually bigger than 1 plus a quarter plus a ninth, because we're adding a little bit on the end. So we can get lower bounds for this thing. And in fact, we can probably get this series to whatever number of decimal places we want just by adding up some finite number of terms. That's the idea of estimating the sum, which we'll get to at the end of this lecture. Let's look at the next example. So this question is asking us to investigate the convergence or divergence of the harmonic series. So we've seen this one before, the harmonic series. We've already seen, however, that it diverges. We looked at one argument that showed that the harmonic series diverges. We're going to look at another argument here, completely independent of the first argument. So here we're going to look at showing why this harmonic series diverges by doing a comparison with an integral. If I look at the corresponding integral, we have that this diverges. So this we knew diverges from a section on improper integrals where we were looking at these things. So this is a divergent integral. What that means is that the area under the curve is infinite. How can I use that information to tell me information about the harmonic series? Well, if I know the area under the curve is infinite, I'd like to realize the harmonic series as the area of some region which is bigger than the area under this curve. Because if the area under the curve is infinite, and I recognize that this can be representing the region that's bigger than that even, then this also has to be infinite. So my choice here is I'm going to take rectangles that sit above the curve. So I'm using left-hand endpoints on each interval. What are the areas of these rectangles? Well, this height here is 1, so the area in this case is base 1 times height 1. The area in this case is base 1 times height, which is a half. The area of this one is a third, and so on, all the way down. That's a quarter. So what we have is that the sum from 1 to n, and going from 1 to infinity, which we're recognizing as the area of the rectangles, that has to be bigger than the integral from 1 to infinity of 1 over x dx. And we know that that integral is infinite. So therefore, this series has to be infinite. So therefore, the series diverges. So that's a nice, quick argument using information we already knew about an integral to conclude information about a series. This is a nice, quick argument to show that the harmonic series diverges. Now, one thing to note between these two examples is it might be kind of surprising that in the previous case, this converges, where all we have is a square on the end, whereas in this case, it diverges. 1 over n diverges. Even though both graphs sort of look the same, the tail end, these values that we're adding on to the end of the series, seem to be very small. This tells us that these values, these 1 over n's, they aren't going to 0 fast enough to guarantee convergence. They're not going to 0 fast enough. 1 over n squared, for any given n, 1 over n squared is smaller than 1 over n. So these things seem to be going to 0 fast enough. We get that because, well, the series converges and we're adding on the infinitely many things. The tail end of the series, they seem to be going to 0 fast enough to not make any significant contributions to the sum and not affect the divergence of it. So it's causing it to converge. So the tail end of the series seems to be going to 0 fast enough to not make significant contributions to the sum. Whereas in this one, the tail end of the series doesn't seem to be going fast enough. This is going to be the running theme with deciding whether a series converges or diverges. It's really a question about how fast do the terms go to 0. Do they go to 0 like 1 over n? If they do, they're not going fast enough. You get divergence. Do the tail end of the series go to 0 like 1 over n squared? Those go to 0 fast enough, so you get convergence. This is going to be a running theme. How fast do the terms go to 0? This particular section is going to answer the question in this way. Do the terms go to 0 fast enough to guarantee the series converges? Well, I'm going to ask that same question about the integral. If the terms go to 0 fast enough so that the integral converges, then it seems to suggest that the series should converge. But if the terms don't go to 0 fast enough so that the integral converges, so then that the integral diverges, then the series should diverge. That's the integral test. The integral test says if you're staring at a function which is continuous, positive, and decreasing, then the question about whether a series converges or diverges is really a question about whether the integral converges or diverges. So let's have a look at this next example. 1 over n times ln of n all squared. Now, one of the things to note with this example, you may say, well, where is this example coming from? Well, the idea is this. We know that a series with terms 1 over n diverges. So the series with these terms diverges. We have that 1 over n squared terms with, or series with those terms, that converges. Now, if we think about this one, I've got a 1 over n, so it looks like a harmonic piece with a little bit extra in the denominator, hopefully to pull the terms down in size at the tail end so they go to 0 fast enough. So this actually sits right between these, n ln of n all squared. That's smaller than this and bigger than this. And so we're really sitting somewhere between a divergent series and a convergent series, and we're wanting to know, do those go to 0 fast enough? Do they go to 0 fast enough? Do they go to 0 like 1 over n squared does, fast enough so that we get convergence, or do they go to 0 like 1 over n does, in which case they still make significant contributions on the tail end of the series and cause it to diverge? So that's where this example is coming from. We've just adjusted taken, instead of an n in the denominator, we replaced it with an ln of n squared, which is smaller than n, and we're still asking the question of does it converge. So just it's not important to really understand that that's the reason I'm asking this question here, because it's not going to depend on this, but that's really the nature of why this question is here. It sort of sits in between this convergent one and this divergent one, and so you're sort of up in the air as to should this converge or should it diverge. So what do we do in this case? Well, what we can do is we can say, well, there's an underlying function here. The underlying function is x ln of x squared. I'd like to use the integral test, so I'd like to know, is the function continuous? Well, I don't need to have continuity everywhere. I just need to be continuous on the interval from 1 to infinity. Does it need to be 1 to infinity? Well, no, because notice that the only role this 1 is holding is the place where the integral starts and the place where the series starts. That can really be anything. We can make it a for any number bigger than or equal to 1. So it's worth realizing that this can be made much more general than stated here. So it can start at any number. In this case, we're going to start it at 2 because that's our n value. So it's continuous on 2 to infinity. Well, where would be the problems? Well, it would be discontinuous at 0, because that's where the denominator is 0. But it would also be discontinuous where the logarithm is 0, and that's at 1. And that's really why we're starting at 2, because there's problems at both 0 and 1. So it's continuous on 0 to 2. Is it positive? Certainly. N is positive, ln of n squared is positive, the reciprocal would be positive, so it's certainly positive on 2 to infinity. Is it decreasing on 2 to infinity? Well, as n gets bigger and bigger and bigger, the denominator is getting bigger and bigger and bigger, so the reciprocal is getting smaller and smaller and smaller, so it should be a decreasing function. Now, in this case, it might be relatively straightforward to see, just by looking at it, that it's decreasing. How would you do this in general if it's a little bit more complicated of an expression? Well, the way you do this in general is, you know a function's decreasing if its derivative is negative. So we go ahead and take the derivative of this thing. Derivative of the top is 0 times the bottom minus the top times the derivative of the bottom. Derivative of the bottom is the product rule, so it's the derivative of the first times the second plus the first times the derivative of the second. So there's a 2 ln of x and an x. And then all of that is over the denominator squared. X ln of x all squared, and that whole thing is squared. There's possibility of canceling those x's off. The question is this positive or negative? Well, for the interval 2 to infinity, so x bigger than or equal to 2, the logarithm is positive, squaring it's positive, adding another logarithm on, still positive. Denominator is a square, it's positive, but there's a minus sign in front. So this thing is negative. So this thing is negative, which means the function is decreasing. So that's how you could do it in general. You just take the derivative and see if it's negative on the interval under consideration, and therefore it's decreasing. So what does this mean? It means that we've got all the hypotheses satisfied for the integral test. So we can go ahead and look at the corresponding integral from 2 to infinity of 1 over x ln of x all squared dx. Now the antiderivative of this thing, we could get it by doing a substitution, u equals ln of x, or maybe you can just spot it by doing the substitution in your head. It's going to be this. And that's from 2. Here I'll write it as an m, and then take the limit as m goes to infinity. Now this becomes the limit as m goes to infinity of negative 1 over ln of m plus 1/2. As m goes to infinity, 1 over ln of m goes to 0, so this goes to a value of 1/2. So what that means is that the integral converges. So the corresponding integral converges. That means that the terms do go to 0 fast enough, because we have that the integral converges, and therefore the series has to converge. So therefore, by the integral test, the series converges. So back here, the question was really 1 over n ln of n all squared. Do those things go to 0 fast enough to guarantee convergence? They're trapped between 1 over n and 1 over n squared, where 1 over n diverges and 1 over n squared converges. Turns out that we have now answered this question. This converges. If you want to play with this idea just a little bit more, then you can try this. Try this one. The sum of 1 over n, and instead of having a square here, because the square in some sense made the denominator a bit bigger, so that perhaps pulled these values, these tail end values, the terms, down to 0 fast enough to guarantee convergence. So what if we relax it a little bit? N equals 2 to infinity. Instead of taking the square on the ln, just n times ln of n. That's going to sit somewhere right in here, between 1 over n ln of n squared and 1 over n. That's this 1 over n ln of n. And so there's a question. Do those go to 0 fast enough to guarantee convergence? And you can, again, apply the same argument, do the comparison with the integral and see what happens. So try this one. Try this one.